is on the plane of loading. Right. What happens is that this is obviously not going to fail on the plane of loading, it's going to fail at this awkward plane. So here is what I'm going to draw next. Okay, here is what I'm going to draw next. I'm going to draw it on that inclined plane. So that's failure plane. This is the plane of loading. Okay, here is the plane of failure. Right? I can draw the state of stress on an area element there, but I don't know what are the stresses that are available there. So I can draw the state of stress. On that volume element. But I don't know what those stresses are, so here is what I do. I say, okay, this area element, is it at the same inclination as this one? Can somebody tell me if that is the case? It's not, right? Obviously it doesn't look like it. So what I'm going to do is I'm going to take my volume element which I just drew, I'm going to slice it at an angle and break open the slices. I'm going to break it this way. Okay, so I'm going to cut it open so that I'm going to get some kind of a triangular cuboid, I don't know what you call that thing, but it's going to look something like this. I'm going to remove this in the meantime. This is, hang on a minute, brittle failure, okay, due to maximum normal stresses. Okay. So I'm going to draw that triangular thing, three-dimensional thing. Okay, so here is the situation. Now, I have broken open this plane, this big plane that I'm shading. Let me call the angle here as the angle theta. Okay, so this is the angle made by the plane with respect to the original volume element. If I say that the area of the shaded plane is capital A, then the area of the planes on the right and then the plane on the bottom is going to be just components of this area. Okay, on the right it's going to be A times sine theta. So if I call this as A, B, C, D, E, and F. Okay, so the area of A, B, C, D is capital A. The area of D, C, E, F is A times sine theta. That's the area, right? Common sense, right? It's a component. Then the area of A, B, E, F is going to be A times cosine theta because it's a projection of this area capital A on the bottom. And the area of, let's say, A, B, E, F is A times cosine theta. So far, so good? Okay. But mind you, as I am slicing through on this face EFCD, so that's probably, let's label it here too. So this is A, B, C, D, E, F. On that face DC, E, F, there is a shear stress which is acting vertically down. If I multiply it by the area, it becomes a shear force. You agree with me, right? So there is a shear stress here. Tau, I'm multiplying it by the area, it becomes a shear force. Okay, so this is going to be A times sine theta, and then there is also a shear stress at the bottom on the face ABEF. That becomes a force if I multiply it by A cosine theta. And now what I'm going to do, and obviously on the plane that I have shaded, there are going to be stresses there as well. And to draw them out better, what I'm going to do is I'm going to view this from this side. So view it from this side. I'm going to get rid of the figure there in the last panel. Bear with me, you'll see where we are heading with this one. I'm going to draw the view, a triangle. So let's call this as B, F, and C. Okay, on the side CF, I'm going to have a force which is acting vertically down. Tau times A times sine theta. On the side BF, I'm going to have another force which is acting into the board, but then I have opened it out, and so this is going to be the direction of that if I'm viewing it. Okay, so this is going to be tau times A times cosine theta, and I'm going to set up a pair of axes, call them as y prime, perpendicular to the incline, and another axis x prime. These are perpendicular to each other, and on the inclined face, which is essentially this area capital A that you're seeing, I'm going to have two stresses. I'm going to have a stress that is normal to the face, and I'm going to have a stress that is along the face. Does this make sense to everybody? On this face, it is kind of hard to show it on this face, on this figure. On this face here, which is what you're seeing here, this face BC projected into the page, you're going to have two stress components. One stress which is perpendicular to BC, the other stress that is along BC. The perpendicular stresses will obviously be your normal stresses. So I'm going to call it as sigma y prime, y prime. And then I'm going to have another stress which is along the incline. I'm going to call it as tau x prime y prime. If I multiply it by the area, these stresses become forces. What is the area of the shaded face? Capital A, capital A. I'm drawing forces, I'm not drawing stresses. This is the figure that had the forces here. From the volume element, I multiply it by the area of these faces, I become a force rather than a stress. I do the same thing. On this total surface area A, I have stresses which are along the incline and perpendicular to the incline. Multiplied by the area, they become forces. All of you with me so far? Okay. It has to be in equilibrium, so I have to perform a force balance. Right? And so for that, I have to break everything into components. So I call this angle as theta. Okay, so this is the angle between the x-axis and the x prime axis. So this is the x-axis. The y-axis is the vertical axis. Okay, so tau A sine theta, I have to break it up into components along the incline and perpendicular to the incline. Okay, so this is tau A sine theta, and then I have the angles. This is theta, so this is going to be theta. So I'm going to have tau A sine theta cos theta. That's one of the components. Okay, then I'm going to have tau A sine theta times sine theta. That's the other component. This is my axis, x-axis. This is the angle theta. If this angle is theta, this is 90 minus theta, so this becomes theta. Okay? Just using components. Do the same thing for tau A cosine theta. In some sense easier. Okay, so this is tau A cosine theta. This angle is theta. I'm breaking it up into components along x prime and y prime. So this is tau A cosine theta times cosine theta. Tau A cosine theta times sine theta. Okay, so these are the components. All I have to do is sum forces up. And for that I'm going to get rid of this particular. Just hang on for a few more minutes and you'll see where we are going with this. Two things I mentioned. One thing, brittle material fails due to normal stresses. Okay, this is one thing that I mentioned. The other thing that I mentioned is that if I have the principal stresses, the maximum normal stresses are essentially the principal stresses, that principal stress will not have any shear stress on that particular plane. So what is going to happen is that this guy has to disappear and this has to become a maximum. Does that happen at the same angle is the question. And that's what we're going to figure out. I'm going to sum forces up in the x prime and the y prime direction. Let's start with the y prime direction. Sum of forces. This is your regular static stuff. Sigma y prime times A, positive. Taken care of that guy. Then I'm going to come to this figure here. I'm going to have tau A sine theta times cosine theta, negative. Okay, that's one. So that's taken care of. Then the last one is tau A cosine theta times sine theta, which is also negative because it's pointing along the negative y prime direction. The A cancels off everywhere. Cos theta, sine theta, cos theta is the same thing. So sigma y prime is 2 times tau times sine theta cos theta. I'm going to remove the middle panel. I'm going to do the sum of forces in the x prime direction as well, just to keep everything in hand. So, sum of forces. In the x prime direction, so I have tau x prime y prime times A. I'll do this a little quickly. Then I'm going to have tau A sine theta times sine theta, negative. And then I'm going to have tau A cosine theta, positive. I'm done with this, done with this, I'm done with all of that. So this is tau A cosine theta is equal to 0. Or if I get rid of the A, bring all the terms to the right hand side. Tau x prime y prime is tau times I purposely written it this way. Notice there is a negative sign because I want to write cosine square theta first and sine square theta next, because cosine square theta minus sine square theta is cosine 2 theta. Okay, that's the reason I wanted to write it up. So this is essentially minus tau cosine 2 theta. All we did was force balance. Now, comes the question. For this brittle material to fail, which of the stresses should be the largest? It should be the normal stress. because that's what experiments tell us. At what angle will the stress sigma y prime be the largest? 45 degrees. Right? Because if I say this is 90 degrees, then cosine 90 is 0. That's vanishing. If I say it is 0 degrees, then sine 0 is 0. So the only place where they meet and not at loggerheads is at 45 degrees. So theta max is 45 degrees, which is why you see that when I take a piece of chalk and I break it out open, I'm just breaking chalks here, you'll see that the angle is 45 degrees. Okay? It's no coincidence. The math works out, the experiments work out as well. Observations, predictions, everything. But importantly, look at this. If this is 45 degrees, cosine of 2 times 45 is? Cosine of 90, it is 0. So when this stress is the largest, this shear stress vanishes, which is why when you have principal stresses, there are no shear stresses on that plane. This is quite fantastic, in my opinion. Because this is proving to us, from a physical experiment that we are performing right here, that this quantity is equal to 0 at theta max. And it also tells me one more thing. Very last minute, I think. I'm going to get rid of the last panel here. I'm going to write down my thoughts. Next class, we'll summarize all of these two for the brittle and the ductile and then move on to Moore's circle. Okay? If you understand these, Moore's circle is just a graphical way of capturing all these math. You don't need to do force balance and so on. You can directly just give the answer. Okay? So, brittle failure. When sigma y prime is maximum, this occurs at theta max of 45 degrees for this particular loading. I'm not saying this is true for all brittle failure, because if I take a piece of chalk and if I just pull it open, the plane of failure is the same as the plane of loading. Because when I'm applying a tensile force, the maximum normal stresses are actually on the plane of loading, not at an inclined plane. This is true for torsional loading. Okay? And when this occurs, tau x prime y prime is 0. And so this proves that the principal planes, the planes containing the principal stresses, are free of shear. So this proves and actually that sigma yy value is the principal stress value. All right. Thank you for your patience. If you have questions, I'll be happy to answer them. Next class, we'll tie up everything and then go on to what your book calls as Moore's circle. Very nice, elegant way of representing it.